All right, today's goals will be very fast. We're going to talk about arcs. What are they? How do we measure them? What's their relationship to chords? And one theorem about arcs. Second goal, we're going to talk about some parts and wholes, by which I mean sectors, which is an area and it's part of the whole area. The length of an arc length, which is part of the whole length of the edge of a circle, which is circumference. And then this green piece, which we call a segment of a circle. All right, what is an arc? You can see it's this red region of the circle between 2 points. This is the notation. Notice above the PQ is an arc-shaped symbol. If it were straight, then what would we be talking about? A chord. Segment PQ would be this chord, but arc PQ, all of the points on a circle between 2 endpoints, that's an arc. It's pretty self-explanatory. All right, we do have minor arcs and major arcs. Minor arcs would be any arc which goes along the edge of less than half of the circle. So from A to B is a minor arc. From A to C is a minor arc. From C to D, if the arc covers less than half of the circle, it's a minor arc. A major arc will be an arc which covers more than half. And you're going to have to use 3 letters for major arc. So arc ABE would start from here and go all the way to endpoint E. You can see it covers about 2/3 of the circle. Arc BEA would start here and go all the way through B and then A. Arc BEA is this entire large part of the circumference. It covers about 80% of the circle's edge. A semicircle would be an arc whose endpoints are endpoints of a diameter. Arc ACD, if you start from A and then go to C and stop at D, you'll cover half the circle, which is a semicircle. The letter in between your endpoints can be any letter on the circle between E and B. So we could have called arc ACD, arc ABD if we want. It's the same semicircle. All right, how do we quantify an arc? How do we talk about its size? Well, there are 2 very different ways of talking about an arc's size. First of all, we can say, what if you were an ant and you were walking along this red path? How long would your walk be? That is the length of the arc AB. That's called arc length. When you use the word measure, we mean something completely different. The measure of an arc AB is the amount of rotation we do in the center so that 2 radii subtend or intersect the endpoints of the arc in question. So the measure of this red arc would be approximately 50 degrees because that's the measure of the corresponding angle that intercepts that arc. The measure of arc AB, and this is the notation we use, a little m in front of the arc symbol. The measure of arc AB is equal to, and this is the definition, it's equal to the measure of the central angle that intercepts it. So the central angle will always be an angle whose vertex is the center of the circle. Last thing here, this statement here is about arcs, but if this statement was about segments, if we said that the measure or length of a segment was equal to the length of another segment, that would imply that the segments were congruent. If these were angles, then when the measure of one angle is equal to the measure of another angle, that would imply that the angles were congruent. However, be careful. If the measure of arcs are equal, this does not imply that the arcs are congruent. And why not? Well, consider this arc AB right here. What is the measure of this arc? It looks like it's about 50 degrees. The central angle is 50 degrees, which means the arc's measure is about 50 degrees. Well, what if we looked at another circle that was only this big? So it was not a congruent circle, had a much smaller radius. But what if we looked at an arc that still measured 50 degrees? Then this would be true that measure of arc AB is 50 degrees, and the measure of arc PQ, if this was P and this was Q, is 50 degrees. So the measures are the same, but are those arcs congruent? Not at all. Arc PQ is a much smaller walk for that ant than arc AB. So just because they have the same measures for arcs, that does not mean that those arcs are congruent. What would it take for two arcs to be congruent? Well, they would have to have the same measure, and they would have to be arcs on congruent circles, or circles with equal radii. We could also say two arcs are congruent if and only if they have the same measure and the same length. Okay, what about arcs and how they relate to their corresponding chords? If you look at this picture, in black we have arc AB and the corresponding chord, which is the segment with the same endpoints. If the black arc and the gray arc are congruent, so if the red is true, then we know that those corresponding chords will be congruent. Similarly, if the arcs are congruent, two arcs on a circle, then we know that their corresponding central angles are congruent. This is kind of trivial because the definition of the measure of an arc is the measure of its corresponding central angle. So if the measures of the arcs are the same on the same circle, then that means the corresponding angles have to be the same as well. So all three of these imply the other two. If the central angles are congruent, then those corresponding chords are congruent and the corresponding arcs are congruent. They all mean the same thing. It's all pretty simple. So here is one theorem related to these things. If you have a blue chord and you have a green radius that is perpendicular to the chord. Let's say that again. If a radius is perpendicular to a chord, then it bisects the chord and the arc. Real easy proof here. If C is a radius, if CQ is a radius, then C is the center, and C is therefore equidistant from A and B. That's what it means to be a circle. All the points that are equidistant from one given center point. So if this is a radius in green, then C is the center, and it has to be equidistant from A and B. So if C is equidistant from A and B, then it must lie on the perpendicular bisector of segment AB. That's the perpendicular bisector theorem from quarter 2. That proves our theorem. All right. Now this is a two-way street. It's a biconditional. So if we had a chord and we constructed its perpendicular bisector, then we know that that perpendicular bisector would have to go through the center and therefore it would contain the radius. I'm going to prove that next slide, but right now a nice application. What if I just gave you a blank circle and said find the exact center? How would you do that? You could kind of eyeball it, but you'd probably be off by a little bit. But using this theorem, we can say, well, let's just draw two chords, a green one and a blue one. Then let's construct their perpendicular bisectors. So the green one's perpendicular bisector and the blue one's perpendicular bisector. We know that the center of the circle is going to be on each of those perpendicular bisectors. So where they cross will be the circle's center. This is a nice proof of the converse that we didn't prove on the last slide. The book offers one proof, but this one's different. It's one of those indirect proofs, a proof by contradiction. It's a really nice logical structure that's very powerful, and we'll use it for the rest of your high school career. So here's what we're trying to prove. If you construct a chord's perpendicular bisector, prove that it contains the radius and therefore goes through the center C. Well, what if the center of the circle is not on the chord's perpendicular bisector? So here we have a blue chord. We've constructed its perpendicular bisector. And what if the center of the white circle, C, is not on that perpendicular bisector? But if it wasn't, then it wouldn't be equidistant from points A and B. A and B. Why not? Because the perpendicular bisector theorem says if you're equidistant from the endpoints of a segment, you must be on the perpendicular bisector. Well, if C is the center of the circle, by definition, it must be equidistant to these points. But that's impossible if it's not on the chord's bisector. That means we've arrived at a contradiction. How can we arrive at something that's not even possible? We made a false assumption. Our assumption that C wasn't on the bisector, the perpendicular bisector, has to be false. Therefore, C is on the perpendicular bisector of the chord. Okay, so for today's goals, we are done with this. We've defined arcs. We've talked about the arc length and the measure of an arc, the relationship to chords, and one theorem. Next, this idea about part and whole, and specifically the area of a sector, which is like a piece of pie, the length of an arc, and the area of a segment. All right, the part whole idea. When we solve these problems, you're going to have a choice. You can either do it using proportions or using fractions. You don't have to learn both. You might understand both, but you probably have a favorite way of doing it. What do we mean by this? If we're going to solve these types of problems, which says, what's the area of that sector? What's the length of that arc? What's the area of that segment? Then we could always just set up a proportion. Part over whole equals part over whole every time. If you like that, it's a great way to go. On one side of the equation, the part divided by whole will be the central angle divided by, which is this measure, the angle on the inside, how much rotation was there, divided by the whole, which is 360 degrees every time. So central angle measure divided by 360 equals area of the sector divided by the area of the whole circle, pi r squared. Or if you're trying to find arc length, same thing, central angle divided by 360 equals the arc length, which is part of the whole circumference, 2 pi r. Maybe you don't like proportions. Maybe you just like fractions. So the part, let's talk about this yellow part, will be a fraction of the whole pi r squared area. What's the fraction that this yellow part is of the whole circle? Well, it will be the fraction of central angle divided by 360. For example, if that were 90 degrees, then 90 divided by 360 is 1/4. If you're trying to find the arc length, same exact thing. What's the central angle? Because that divided by 360 would be the fraction of the total arc length, circumference. That would give us the arc length that we wanted. All right, let's see a couple of examples. Here we go. Find the area of this black sector when the radius is 100 and the central angle's measure is 40 degrees. So if we use the proportion, the area of the black sector divided by the whole circle, pi r squared, equals the central angle 40 degrees divided by the whole central angle 360 degrees. When you solve this, we get 10,000 pi over 9. If you prefer, the area of the black sector is a fraction of the circle. The circle is pi r squared. What fraction? 40 360ths. What about the arc length of this? Whoa, I didn't mean it to be that big. how far is it on the edge from here to here? So as a proportion, that is a part of the entire arc length all the way around the circle, 2 pi r, the circumference. Just as 40 degrees is a part of the whole 360-degree rotation. When you solve this, we find that the arc length is 200 pi over 9. And if you preferred, you could have said the arc length is a fraction of the whole circumference. What fraction? 43/60. All right, finally we get to a segment, which is this blue region. Well, you might have already figured this out. To find the area of that strange shape, which is not a circle, a sector, a triangle, a polygon, or anything, we will take the area of the entire sector and then we'll subtract the triangle. What will be left will be our segment. So the sector is pretty easy. I'm going to use the fraction method. 98/360 of the whole circle's pi r squared. And then for the triangle, this one's going to be kind of difficult. This triangle, all we know is that it's isosceles because the radii of the circle are congruent, and that vertex angle is 98 degrees. I'm going to flip it over into this orientation. The radius is 12, which means 12 here and 12 there. 12 here and 12 there. So 12 and 12. And a 98-degree central angle, which is on the top here. So if we split that straight down the middle with a segment that's perpendicular to the base, we have the height. 98 degrees divided by 2 is 49. 90 plus 49 plus 41 gives us the 180. So to find the height of this triangle so we can find the area, let's park at 41 degrees. That's opposite over hypotenuse. So sine of 41 degrees is h over 12. So that the height is 12 sine of 41. Now we need the base, which is all the way from the left to the right, but we're going to use half of the triangle, which is a right triangle, to figure out x, and then we'll double it. So this, if we're parked at 41, is adjacent in hypotenuse, so that's cosine of 41 degrees equals the adjacent divided by the hypotenuse. So x is 12 cosine of 41. So the base of this triangle is 2 of those, which is 24 cosine of 41 degrees. All right, so the area of this triangle is 1/2 times the base times the height. And when we simplify 12 squared divided by 360 and then 98, we get 39.2 pi minus half of 24 is 12. 12 times 12 is 144. Cosine of 41, sine of 41. So this is the exact answer, which is simplified. We can't get any simpler than that. And if we approximate with our calculator, it's approximately 52 square units. That's it. Tried to be quick. Go ahead and rewind and rewatch that, but that covers all the bases. And as usual, read the text. Section 12.2 and 12.3.